Hello, hello. Hello, Unite, and welcome to this talk about going multiplayer, how to help your studio and game thrive. In this talk, I'll show you how to avoid some common mistakes, common but not obvious mistakes, in order to increase your chances of success in the world of multiplayer games. But first, let me introduce myself. I'm Paolo Abela. I'm a senior software engineer at Unity and technical lead of Fatus Games. I have more than 11 years in game development with several single players and multiplayer titles released. And I'm also the author of this little book, 5 Expensive Mistakes That Your Multiplayer Team Must Avoid and How to Fix Them, which kind of inspired most of this talk. So the agenda today is to go through these 5 little topics. The best netcode framework, what is the best netcode framework, when to implement multiplayer, how to do proper data synchronization, how to optimize your server builds, and how to run your server builds properly once you have optimized them. If you have questions, don't worry, we'll have some Q&A at the end, so just write down the questions so don't forget about that, and then we'll have some time at the end so I can answer those. So, let's start with the first one. The best netcode framework ever. What is the best netcode framework ever? This is a question that I get every time. And before we answer that, I want to be sure that we all know what we are talking about. So, first of all, what is a netcode framework and why do we need it? A netcode framework is basically a code library that allows you to implement the multiplayer features of your game. So we need it to connect players with each other, to send data around, and to spawn objects over the network so they can get synchronized. An example of a netcode framework is Unity's Netcode for Game Objects, but there are many. And when we talk about netcode frameworks, we are talking about what happens in the game, not what happens in the metagame or around the game. So we're not considering things like matchmaker, authentication, or how you spin up and shut down dedicated servers. These are commonly referred to as backend services, and they are another thing. They are usually integratable and with many different frameworks. They are framework agnostic and vice versa. So they're not the topic that we are discussing here in this moment. Let's focus on the netcode framework and what happens in the game. So back to the question, what is the best netcode framework? You could ask 100 studios about that, and nobody will ever tell you something like this. Nobody will ever tell you, I picked a random netcode framework, and it just worked. And that's for a simple reason. Because different games require different types of optimizations. And the best netcode framework changes depending on your game. So I was saying, different games, they are not born equals. They require different features. They require different optimizations. So there is a limit to how many of these optimizations and features can be bundled in a single netcode framework without making the development experience complicated for you, without giving you too many options that you have to tweak in order to have something playable. So if a framework claims to be the solution to all the problems, don't trust it. It's probably a jack of all trades and a master of none, and it won't allow you to implement all the features of your game. And this is a problem because choosing the wrong netcode framework will limit what your game can do. Let's make a practical example. So this is Mario. Mario is an imaginary studio lead at a fictional studio that does not exist. And they released a couple of single-player games, successful single-player games, with this team of veterans. Okay, they know how to make single-player games. They have no idea how to make multiplayer games. But they want to make one. And they don't know how to get started. So they started educating themselves. And one day, Mario is doom-scrolling on LinkedIn. And he comes across a post about how somebody managed to make a competitive card game using netcode for game objects. So he goes back to his team, super excited, and says, hey, guys, we'll make a 100 players battle royale game with vehicles in 6 months using netcode for game objects. And there are 2 problems here. The first one is the 6 months, first of all. setting too high expectations. And the second one is that netcode for game objects is not built for this type of games. So he saw that somebody used it to make competitive games, but there was like the card part that was very important. So what happened 6 months later is that they start playtesting over the internet with real players, and they complain all the time. They complain all the time because the vehicles are rubber banding, because they move too fast, so they go ahead and back, ahead and back. And then they try to shoot at other players, and they can't hit them. And why is that? Because netcode for game objects is not built to support this type of super fast-paced gameplay at that scale. And so what happens is that the internet messes things up because there's latency, because there's lag. So this little mistake costed Mario, let's make like an example, okay? Imagine that Mario has This team of 5 veterans, it costs him 50K per month. They spent 6 months making this prototype that doesn't meet user expectations at all, so it needs to be scrapped and redone. So they wasted something like 3K of budget, and most importantly, 6 months, just for a single bad choice. So how do we avoid falling into Mario situations? How do we pick the right netcode framework for our game? We need to ask ourselves some questions. Okay, we need to ask ourselves how many people are going to play this game in a single session altogether. What is the pace of the game? Is it slow-paced? Is it fast-paced? Is it turn-based? Is it asynchronous? Like, there are many options here. Does it have physics? Do we shoot at people? Do we jump? Do we run? Do we have gravity? Do we throw grenades? Do we throw spears? These kinds of things. How many networked entities are going to be there? Because it's not just about the players, but it's also about the non-playing characters, like pickable objects. Everything that needs to be synchronized needs to be taken into account. And in the end, what features were we going to implement? Okay. So I prepared some examples here to give you a better understanding and a starting point if you're making something similar to those. So let's start with the first one, Apex Legends. Apex Legends, for those who do not know about that, it's a battle royale game. You have 60 players in a single session trying to fight each other until only one remains. It's fast-paced, it's physics-based, people shoot around, jump, and so on. And you have a lot of networked entities, most of which are players. And the problem with players is that they are unpredictable. They do actions that you can't really predict. You can't predict how they are going to move. You can't predict when they're going to shoot. That's what humans do, right? So in this case, we need something that is both able to support that large scale of players over a large map and a set of optimizations needed to show and hide players and objects depending on how far they are from your allies or the local player. So in this case, something that could be helpful is netcode for entities, for example. Another case is Wild Rift, League of Legends Wild Rift. It's a totally different game. It's a MOBA, so it's 2 teams of 5 players fighting each other on a relatively small map. It's still fast-paced. It's not really physics-based, or not, at least not in the same way Apex Legends is, but it still has a lot of network identities. And the difference here is that most of those are non-playing characters. So they can be predicted. Like, you can calculate client-side, so not on the server, but on the client, what they are going to do. Okay, and this makes things way, way easier. So we still need something that supports the fast-paced aspect, but we don't really care about the huge number of players there. So in this case, something like Fishnet would be a better option. And then we have another completely different game that is Aryokan. This is a game I'm working on at Fatus Games. And it's a collectible card game where players can create their own cards at any time. So it's a 1v1 game. There's only 2 players per session. It's turn-based, so it's super slow-paced. You play basically like chess. I make a move, you make a move. Rinse and repeat. It's not physics-based because it's just UI and cards, so we don't have any things. And the networked entities here are just the 2 players and what I call cards alterations, which is basically what changed from a card since the game beginning, like all the buffs and debuffs. So it's a very completely different game. And what is important here is just the server authoritative aspect, the how do I prevent cheating aspect. So all I need to do is validate inputs on the server and basically make sure that the data travels safely and reliably between the 2 players and the server. So I don't need the fast-paced aspect. I don't need the large scale. All I need here is stability and anti-cheating, and that can be provided by a framework like Netcode for game objects. So what would happen if I made Aryokan with Netcode for entities, like with a framework that is suitable for Apex Legends? Well, I could still make it because Netcode for entities is very powerful, but that would be like overshooting, overkilling, right? It will be using something that is too much for the job that you need to do. It's like going to the grocery store with a Ferrari. You don't do that, okay? So, but I would still be able to make my game. If I did the opposite, like if I tried to use Netcode for game objects to do Apex Legends, I will be in Mario's situation. I will be problems with fast-paced gameplay. So once we understand what type of framework we need to use, the question that comes after is, okay, so when do we implement multiplayer? And this is where many, many studios like fail at making the right choice because they treat multiplayer as a second-class citizen that can be added later. So whenever somebody says, I'll make the single-player version first, and then I'll add multiplayer later, you can be 100% sure that they're going to waste a lot of months reworking everything once they get to the implement multiplayer part. And that's for a simple reason, because unless your gameplay has 0 multiplayer features in it, you need to architect the entire game, considering that one day it will go on the internet where latency exists, problems come, things can and will go wrong, packets of information get lost. So, and states and inputs need to be validated to avoid cheating. Again, if you care about avoiding cheating, if you're making a casual co-op, couch co-op game, you can completely forget about that. Nobody cares if somebody cheats when you're playing Brawlhalla. But if you're making a competitive game, if you want to have ranked leaderboards, if you want to have competitive season, then cheating is extremely important. Let's make an example. Let's make an example of this situation where somebody makes a single player first and then tries to convert it to multiplayer. So let's assume that you have a single player post-apocalyptic survival game where you have 3 main features, like you can do missions to gather resources, you can recruit survivors that help you in the missions, and you can build and customize your outposts with what you get from the missions. So when this is single player, pretty easy. You make the vertical slice, you go to your publisher, you show it to them, and they are like, oh, wow, this is super cool. Now, can we make the multiplayer version of that? Because that's what the market wants. So what happens now? What happens is that you need to rework the entire game to change these 3 features in a way that works with the internet. So for the missions and resources, now the resources and the missions need to be synchronized and manage it server authoritatively to avoid cheating. Otherwise, what's stopping a player from saying, I want to collect all the resources that are in the map without moving? Nobody. So you need to implement that. Or even to unlock rewards from missions that they haven't unlocked yet, that they haven't reached yet. So that part needs to change. Recruiting survivors, it's a multiplayer game, right? So we want other players to join the missions. And that means that we now have to manage the fact that there's other humans that want to see what's happening in the game in real time. And that means that when somebody shoots, I want to see them shooting on my device as well. I can't just shoot locally and make zombies fall dead around me. So I need to synchronize all the actions, but also the movement. And the problem with the movement is that whenever a player moves, it takes time for that input to travel from his device, their device, to the server and to get relayed to all the other clients. So whenever you have this latency, this time that it takes, you will see something too late compared to when it happens. So we need to implement some algorithms here that kind of rewind the state of the game and re-simulates it as if the input started at the moment at which it really started. So this gets things way, way more complicated. And then for the building and customizing your outpost, well, imagine that if you have your own outpost, you of course want to see other people's outposts. You want to help them, you want to attack them. So you need to be able to have a system that allows you to interact with other players' content, to store this content into the cloud and make it centralized so it can be secured. So as you can see, this is a completely different game from the single-player version. In the single-player version, you can just save all this information into a file, like a local file. You can have some local checks, and who cares if somebody cheats? It's a single-player game, right? No problem. But to implement all those things, you need cloud services, you need backend services, you need server authoritative logic. So it changes things by a lot. And this is super important because nobody cares if you're cheating in a single-player game. But when there is multiple people involved, when there is emotions at stake, people can get angry, will get angry and frustrated if somebody cheats and ruins the fun for them. And guess what? Angry players stop playing your game and go playing your competitor's game. And that's exactly something that you want to avoid. So when do we implement multiplayer? If we want to implement multiplayer in your game, be it immediately or in the near future, like if you already know that this game one day is going to be multiplayer, you need to implement it from day one. And all the features must be designed in a way that they can survive the internet, so they can work in a networked environment where, again, latency exists, and also people have different, devices have different roles. There could be clients, which is from where people play. There could be the server, which is from where the logic is checked and the inputs are validated. And there could also be the host. Host means that you have the server and client on the same device, and you connect with the client to the server. And this host mode is also a trick, a very smart trick that you can use to develop your game in fake single-player mode. What does that mean? So it means that you're connecting to yourself, right? So you're basically playing there with yourself, and there's no latency because information doesn't even leave your device. But that forces you to implement features in a networked way. You still need to have the server part and the client part, and they need to interact with each other. So it's a cool hack that you can use to have single-player gameplay, but a network architecture that is easily scalable for when you have 2 or more players. So this makes way easier to launch your game as a single player and to evolve it into a multiplayer game. And your users will never even know about that. Only you will know, and that will make life easier, way, way easier for you. Most importantly, it allows you to inject artificial latency and to test how your game reacts when there is latency. Like, how does my movement work when the input gets processed 200 milliseconds later? And that makes all the difference in the world. Like, if you read the negative reviews of multiplayer games on Steam or on any platform, you will see that 80% of the time, it's always people complaining, oh, this game lags. Oh, I shoot at things that I can't hit them. That's because the multiplayer implementation didn't take into account that the internet exists and that the information travels very fast, but still needs some time to travel. And one common objection that I get when I tell people to implement that is, oh, but we don't want players to go against each other from day one. That's why we don't want to implement multiplayer. But these are not two concepts that fall into the same sentence. Like, you can still have your multiplayer architecture. That doesn't mean that your that your player versus players game modes need to be there from day one. You can still have players play with alone with bots. But what's important is that you have the architecture in place. Because again, adding multiplayer later on is a huge risk, a very huge risk. And I have like 3 different teams that I worked with that made this mistake and then came to me to fix this situation. I was like, yep, we need to change a lot of things now. OK, so now that you know what to use, pretty much, and when to implement multiplayer, the next question is, how do we optimize the costs? And how do we make a good user experience for our players? And this brings us to proper data synchronization. Now, when we're talking about proper data synchronization, there's a super common mistake that all teams that are new to multiplayer do, which is that they try to synchronize everything. They say, oh, yeah, we just synchronize everything, so everybody has all the data, right? Nope. That's exactly the problem. Okay. So the only things you need to synchronize are state and events. State are variables. Okay, my power is over 9,000, for example, or I have 10 health points. Events are the actions that your players are doing, not the inputs, the results. Like this guy is pressing a button on the wall, or this guy stepped on a platform, okay, these kinds of things, or I am shooting. What you don't need to synchronize is everything else. UI, visual effects, textures doesn't mean anything. Okay, it's not needed. But why? For a simple reason, because all the other data can be retrieved deterministically locally on the clients if you send the right data from the server. What does that mean? That means that you don't have to spawn the visual effects. You can just tell the clients that an explosion happened, and then the client can spawn the visual effects. So now let's make another example. Let's talk about Mario's team again, because they ran out of money, so they're now trying to make something simpler, right? Smaller scope, a clone of chess. And let's start with the super wrong approach that the beginner team would use, which is to synchronize everything, to understand why this is a problem. So in chess, we have 2 players. They have 16 pieces each, like the black and the white. So in the beginner approach will be to synchronize all of those, plus the board, because of course we want players to see the board, right? And then since everything is server authoritative, because we also want to avoid cheating, we tell the clients when to play visual effects, we tell the clients when to play sounds, when to move or destroy something. So every time a player wants to make an action, they need to ask the server, they need to wait for the server to say, yes, you can do that, or no, you can't. And then they play the animations, and then they play the sounds, and they play everything. So what's the problem with this? The problem is that this doesn't work for 2 reasons. First reason is that the user experience is terrible. Every time you need to wait for the server, you are subject to the latency issue, right? So imagine if you had to wait every time you wanted to move in a game for the server to say, yeah, you can move. That would be terrible. Like if it took 100 milliseconds every time, it would be terrible. So this is terrible from a user experience. But also the board, if it's synchronized, it means that it needs to be spawned on the server. And since it's part of the UI usually scales based on the desktop resolution or the screen resolution, right? And what resolution does a server have? A server doesn't have a screen, so we don't know. So what happens is that the UI might have issues scaling, and also it will look like the same for every player, but this is what the white player wants to see. The black player wants to see the opposite. They want to see the black pieces at the bottom. So this approach doesn't work. What is an approach that works? The standard one. The standard one means that we synchronize 2 objects per players, the 2 players, and then we have one networked object for each piece, and for each of these objects, we have some data that we synchronize. We synchronize the position, we synchronize who the owner is, we synchronize if the piece is alive or dead, if it's still in play. And then for the UI, we use something called prediction, for the user experience, sorry, we use the prediction and reconciliation algorithm, which is something extremely important in multiplayer. How does that work? So prediction, the prediction part, it's client-side prediction. It means that whenever we make something, we try to predict what the result will be based on the action. So if I try to move one of the pawns in a square that is empty, I can calculate if that's a valid move because I know the rules, like the client knows the rules as well. So I can predict that the piece will end up there. And at the meantime, so I immediately play the animation, I immediately play the sounds, and in the meantime, I tell the server that I want to do that. The server makes his calculations, makes his validation, and then gives me a result. It tells me, hey, yeah, okay, you can do it. Or no, you can't. If it gives me the same result that I predicted, then I don't need to do anything. I already did what I needed to do. And I did that immediately, no latency. Super good user experience. If the server corrects me, then I need to fix the situation. I need to adjust the piece. I need to bring it back, for example. And this happens very fast, usually. So the user experience is great at this point. And what about the UI? What about the board? The board, we need to instantiate that locally. So we need to have some initialization logic that is different depending on who the local player is. So this is where the multiplayer challenges start. Like, you need to change how the game behaves depending on if I'm player 1 or player 2. But it's doable. And what is the outcome of all of this? The outcome is that we have a working game that kind of uses around 3 kilobytes per second in order to synchronize all this data. We are assuming that we are not smart about the data. We are sending everything and synchronize everything all the time. So with a tick rate of 10, which means that we send this data and synchronize it 10 times per second, that's what we consume. But there is a better approach, which is the professional approach. And the professional approach requires us to be a bit smarter about the data and how we architect our game. So we still synchronize the 2 players, but now we don't synchronize pieces individually. Instead, we synchronize the board state. And what is the board state? It's basically the state of each of these squares in the board. So it's an array of 64 squares, and we use a byte for each square. And a byte is made up of 8 bits. So that means that it can have 256 values, ranging from 0 to 255. And that value tells us what is in the square. So if the byte value is 0, that means that the square is empty. And it's the case of these yellow circled squares that you can see in the middle. What if a byte is between 1 and 127? That means that it's a piece of the first player. So the information that we used to have in a flag is now implicit. Okay. And that tells us exactly what piece is that. Piece number 1 is different than piece number 27. Okay. And the same goes for the values between 128 and 255. That's a piece of the second player. So this is pretty much the same logic that we have in the other example. So we don't synchronize the UI, we don't synchronize everything that we don't need to synchronize, but instead we are smart about the data, and you can see that this approach uses way less bandwidth per second with the same tick rate. And that's not the only thing. Because yes, it's 5 times cheaper from a bandwidth perspective, but it also allows us to have 8 times more content with no bandwidth increase. So these are great stats to tell to your executives or to your design team when you are designing and negotiating things, because that means that the company spends less, 5 times cheaper, and that you can have more content, so your designers are going to be super happy about that. All right. So once we have an idea of how we have to synchronize our data and how we have to model our data, the next step is how do we make a server build that is optimized? And again, you need dedicated server builds only in the case where you care about cheating. If you don't care about cheating, you can use client-hosted models, you can use peer-to-peer, you can use relay, whatever. Okay. But if you want to make competitive games at scale, dedicated servers are the way, pretty much. So how do we optimize dedicated servers? First of all, it's important to understand that it's very easy to make a server build and to upload it as is. You can do it today. But it's also very expensive in the long term. And let me tell you why. First of all, because servers don't need to make most of the things that their client counterparts need to do. Servers only need to do 2 things: validating input and sending information around, like connecting all the players. And so that means that all the visual effects, the media files, the soundtracks, the textures, the animations, all those things, they don't need to exist on the server. The server doesn't need them. There's nobody watching the gameplay on the server. There's nobody on a keyboard typing there on the server. So if we keep those assets into the build, what happens is that we face all these dire consequences. Like we have increased build times because we still need to process the assets during the build process, right? And if you use something like a CI/CD, continuous integration, continuous delivery service for build automation, like every time you make a push, every time you make a change, you make a build, that means that you need to run that process for a longer time every time. And usually that bills you, like you will pay for that. So it's something that you want to avoid, first of all. Then you will have bigger builds. And when you go and do the patches will be slower because we'll need to compare two files that have a lot of media data into that. So increased storage costs, longer patch times. Also longer load times, because if you have these assets in the build, they will probably need to be loaded at some point from disk. And in the best case, this makes your server go slower. In the worst case, it freezes, and your players won't be happy. And then we have like an obvious RAM and CPU waste, because you need to do the loading, because you need to store the information once it's loaded. And again, in the best case, you're going to pay more for your servers. In the worst case, you're going to exceed your usage limits per instance, and the server is going to crash. And when your server crashes, your players are not happy, and they go play your competitor's game. So how do we do this? How do we fix this? In Unity, it's very easy. You just need to use the dedicated server build target. It automatically strips out a lot of this information. It replaces it with like one empty pixel texture, for example. And it does that just for that build. So you don't have to worry too much about this if you use the dedicated server build target. It does pretty much 90% of the job. You can still do some optimizations, though, which are pretty important, which is making sure that all your networked objects do not include media files or visual effects or textures and so on. So that means that you need to strip out manually from the prefabs, for example, of the player, the models, the visual effects, all these kinds of things. You can put them aside. You can put them in non-networked objects, maybe put them in a local database, in a list, something like that. And then you can reference it at runtime. You can retrieve it at runtime based on some kind of ID. So again, an explosion happens. Okay, player shoots something, an explosion happens. The server knows that the explosion happens and tells the players, hey, an explosion happened. And then the client says, oh, okay, an explosion happened. I need to instantiate the explosion visual effects in that specific point. Pretty much that. So we have good server builds. We are ready to upload it. We can finally make our players play, but we also need to do one little change and improvement before we are ready to go for scale, for large scale, which is running the server builds properly. This is super important to increase your runway. So here we can apply like 3 different tips, very easy. The first one is to limit the frame rate. If you do not limit the frame rate, and by default it's not limited, your server will waste all its CPU time processing as many frame updates as possible. So that means that all the CPU will be trying to process frames, even when it's not needed. Okay. And this impacts 2 things. It impacts the cost of the hosting, because you will see the CPU usage going very high, and they will bill you for that, in the best case. In the worst case, it crashes at the end. So it impacts both the cost of hosting it, but also the tick rate. Because imagine this, if you have a tick rate of 10, that means that you have 1 tick every 100 milliseconds, so 10 times per second, okay? But if the CPU is busy doing other work, it might not make it in time. It might not take 100 milliseconds to process a frame. It might take to process a tick. It might take 200 milliseconds. So that means that your effective tick rate becomes half of it, becomes 5. And that means that all the network simulation, the synchronization, the validation of input, the relaying of information is 50% slower. The impact on the user experience of this is devastating. So you really don't want that to happen. Okay. So what is the right cap here? The right cap depends on the game. So you need to test. The right range is usually between 20 and 120 frames per second. And what is important is that the tick rate and the frame rate, they can be the same, but usually they must not. Usually you don't want a 120 tick rate when you have a 120 frames per second. Like tick rate is super expensive to raise. So it also eats CPU time. So keep in mind that, because it's a common misconception. How do we limit the frame rate? 4 lines of code, pretty easy. Dump this on a server object, and you're done. You just need to disable vertical synchronization, because we're on the server, we don't need it. And we need to set the target frame rate of the application. Easy peasy, lemon squeezy. The operating system, tip number 2. So when we need to choose what infrastructure we need to use, we need to usually choose also what operating systems our servers will have. And we have 2 options here. You have Windows servers and Linux servers. Windows servers are usually easier to set up because mainly, especially if you're developing for PC, you usually have a Windows build of your game available. You know that your game works on Windows. The problem is that Windows requires that you pay a license for the operating system. On the other hand, the Linux system is faster and cheaper and doesn't require to pay for the license. But at the same time, you need to be sure that your game works on Linux. So there might be complications depending on like how you read files, for example, and the paths that you use. So you need to start this multi-platform conversion and validation early on in the development process to be sure that your game can be run on both. And to give you an idea of what's the cost of this decision, let's take into account, and as a reference, the cost of game server hosting, Multiplay, the Unity service for dedicated servers. So for Windows, for a single machine running all day, all year, you pay around $400 per year, just for the license of a single machine. The more unoptimized your server is, the more machines you will need. So that cost can quickly scale. And it will scale, like it will be painful to pay that. For literally no value, like the only value is that you don't have to make a Linux build. Linux is free, easy peasy, again. So that's something that you can really avoid paying if you start the conversion process early on in the development. And then tip number 3 is to run your build in headless mode. Headless mode means that we are not initializing the graphic device and all systems that elaborate inputs, like local player input. And why don't we need it? Because again, we are on a dedicated server. There's no screen. There's nobody watching. Okay, so we can avoid these things. And in order to run your game in headless mode, you need to use these launch parameters in Unity. Keep in mind that the batch mode will also, the no graphics will also disable the logging. So you need to manually re-enable that. And it's pretty safe to use headless mode, except one case. The case in which your gameplay needs a GPU on the server side to do some kind of like real-time mesh alterations, for example. In that case, you can't use headless mode because the GPU won't work. But 99% of the time, you should be good with this. All right, time to wrapping up and to remember some things. First of all, pick the right framework for your game. There's no universal best framework. There's the framework that is right for your game. Okay, keeping in mind all the features I need to implement. Implement the multiplayer architecture for day one if you don't want to throw away your project and redo it from scratch, because multiplayer is not an add-on. You cannot add it later without a lot of effort. Only synchronize the state and the inputs. You can forget about everything else. Use local lists, IDs, whatever, to retrieve information that the server doesn't need to know. And also remember to remove all the assets, all the media assets, all the effects from the server, because again, there's nobody watching. And then running your servers with uncapped FPS on a Windows machine is a very bad idea. If you love yourself and your budget, don't do it. All right, thank you so much for being with me until the end and for listening to all of this. If you want to keep in touch, you can do that by scanning this code. It will lead you to my LinkedIn profile, or you can simply add me. That's my name, Paolo Abela. So now we have some time for the questions. Thank you so much again.